So you've got the exponent operation there, you've got the opposite operation there, and so forth. And A is just called the unknown. But then all of a sudden they say, oh, by the way, put in a -7 for A, and then 7. So it's just substituting a number for a letter and seeing what happens. But it's a little subtle. And the reason is it's the exponent. The exponent applies to what is immediately to the left. Okay, what's immediately to the left is A. Okay? However, now you're going to make A a -7. Meaning that this minus sign has nothing to do with that. This minus sign means opposite. It stays there no matter what the number is. Now we know the number that we're going to put in for A is a -7. Well, if we did this, it would be very confusing, not only to us, but to everybody else. You know? What we really need to do is say, I want the -7 to be the base of the exponent. So put parentheses around it. That makes it clear. So what's being squared? -7. And then you've got this other operation out here, which is completely independent of that. It just came with the expression. Huh? So at this point, we have to say, okay, I have to do the exponent next, which means I have to take the opposite of -7 times -7. Okay, that's a lot of minuses. That gives you a +49, minus times a minus. But then you're taking the opposite of 49, and the opposite of 49 is a -49. Okay, so that's what you end up with when you do A equals to -7. And when you do A equal to 7, you get -7 squared. Once again, I would put parentheses in there. It just makes things a heck of a lot clearer. So this becomes the opposite of 7 times 7, which is the opposite of 49, which in this case gives you the same answer, -49. This problem is all about getting the notation clear in your mind and using the notation. But if you use it, you do get right results. But it's probably something you're not used to. It's very technical, very nitpicky. And you got
I have a question though. I have to ask if A or B. If A represents -7 or +7, so wouldn't it be +7 because of negative times negative is a positive?
All right, which one are you looking at? -7 or +7?
For 17, it's like A represents -7 or A equals 7.
Right. So the question, which one do you want to look at? There are two different situations. One is with A equals to -7, the other one's with A equals to 7.
Well, it says -A squared for A or B, and I was thinking B because if we have A squared, that's, never
Okay.
mind, I don't know.
It's the concept of evaluation, okay? When you're evaluating something like this is what you're evaluating, this thing right here. In other words, evaluate simply means get a number for it, okay? When A is equal to -7, here it is, turns out to be -49.
Oh, okay.
And then go back and put in A equal to 7. Well, it turns out in this case to be the same number.
I thought it was asking what -A squared, like -A was the number squared.
No, the negative isn't squared.
Oh.
That's the point. With exponent notation, the exponent applies to what's immediately to the left. Only the A is immediately to the left. The minus sign is not. Okay? So you've got to square the -7. If you're going to use this, A equals to -7, you have to square the -7. And then also take the opposite. Now, when you're squaring the +7, you still have to take the opposite. In this case, as I say, they turn out to be the same. They won't always be like that.
Yeah.
So that's the notation idea. They give you an algebra expression, and that's you put numbers in for it. And then they give you several numbers. Here they give you two. -7 and +7. That's the nature of an evaluation problem. You're stuffing numbers in for letters. Okay, any others?
31. 31.
Okay. Okay, number 31. A is equal to pi times r squared. We've seen that before. And they say let pi equal 22/7. That's the fraction approximation for pi. Not very good. R is equal to 7/2. All right. So once again, we're stuffing in numbers for letters. That's all that's happening here. We're going to replace the pi with 22/7. And the r is going to be replaced with 7/2, but it's squared. So put parentheses around it, 7/2, and put the squaring. What happens with the parentheses in an exponent? You're forcing the entire thing to be squared then. Parentheses override everything, huh? Sandra has something buzzing. I think it may be the hearing aids. Okay.
Do you want me to turn them off? She said, do you want me to turn them off?
Well, it's quite loud.
I think it's outside.
It's all over.
Oh, sorry.
In my English class, it was the same
I
way.
think it's coming from the,
Construction.
Oh,
The
I don't
speakers,
think-
yeah.
actually,
and they just
There
turned
goes that
off.
idea.
She's gonna get new ones anyway, so, yeah.
Okay, great. All right, so what we're doing here is saying, because I put parentheses around the 7/2, the entire thing is going to be squared. If I did this, look what happens if you don't do it. Okay. Now, what's next to the squaring? The 7, but not the 2. Okay? So you're going to square the 7, but you're not going to square the 2. That's going to be a completely different number. And that's not what's meant. The r here is the entire thing. It's 7/2. That's an unusual way to write the radius of a circle as a fraction, but that's what they gave us. We have to go with what they gave us. So the idea here is that's got to be in parentheses. So this is really a practice in using parentheses, okay? Now let's go ahead and do it. All right, so we've got 22/7 multiplied by 7/2 times 7/2. This is what squaring 7/2 is. It means multiply it by itself. Okay, can we cancel? Sure we can cancel. That goes out, 1 over 1. This goes into there 11 times, and so forth. So what do we get? Well, on the top, we have an 11 times a 1 times a 7. That gives us 77. On the bottom, 1 times 1 times 2 is 2. And there's the answer as an improper. If you want it as a mixed, you can do that. I don't, do they want that? Let's see. No, they leave it as 77/2. Okay? This is getting used to the notation of algebra, and the parentheses are very important aspects of it. We're not used to using parentheses too much in English. It has some uses, but most people don't use it. But in math, you really do have to use them because they are very important. They're the power thing. You know, they allow you, the user, to say, do this first. Yeah.
Instead of using the 7/2 times the 7/2, could you just use 49/4 and then cancel out? Or is this?
Yeah.
Okay, I
It's
just
the
wanted.
same thing.
Okay, I just wanted to make
It's
sure.
just that here, I think the canceling is even more obvious if you use 7/2. Yeah, okay. Any others?
11.
The price of gas has doubled over the last 3 years. It's an old If gas cost G dollars per gallon 3 years ago, write an expression for the current price per gallon. Okay, so they're telling us that G dollars per gallon three years ago. Okay. Currently, we know it has doubled. All right, that's an English jargon kind of word, and that's no good for us. We need to have some sort of mathematical understanding of that. Doubled means what? Mathematically.
Twice. Twice?
Twice, okay. What does twice mean? It's still not mathematical.
50%.
No? You can talk about it in terms of a percent. But multiply by 2. That means multiply by 2. Okay. Do you know what triples would be? By 3. And you know the old word for that? Anyone know that? It's thrice. Thrice. We don't have that. Okay, so here it is 3 years ago. It's doubled, which means multiply by 2. Therefore, magic now. I'm going to take 2 and multiply it by g. And that's it. That's the price now. Okay? Price today.
2 G's, 2,000.
Right. All they're doing is asking you to take English and put it in math. That's all it is. Any others? Okay, a minus 4 multiplied by this thing in parentheses, r minus s. But that thing in parentheses is squared. And here they give you r equals 8 and s equals 6. All right, let's put those numbers in. Again, we're stuffing in numbers for letters. So the minus 4, of course, remains what it is. R now is 8. S is equal to 6. Okay, now we have to use PEMDAS. I mean, if you want to get a right answer, you have to use PEMDAS. Okay, and it says you've got to do what's in parentheses first. So 8 take away 6. We're not going to go through the whole thing. We know that's 2. But the 2 is squared. We haven't done the squaring yet, so we have to keep the squaring in the notation to remind us to do that. So a 2 squared, of course, is 4. Finally, we get to do the multiplication. That's lower than exponent. Exponent has to come first. Okay? And therefore, we get a negative times a positive. That would be a negative 16. Okay? Make sense? All righty, any others? Okay, so we're getting used to this, watching notation very carefully. Now, what we didn't do yesterday is the last of the 3 laws. And this turns out to be the most important one for algebra. We talked about commutative law for addition and multiplication. That means simply change places, change the order of things. And that's fine for addition and multiplication. Then we also talked about associative law, which happens when you're adding or multiplying more than 2 things. You can associate the addition and multiplication with anything you want. That's what it amounts to. That's good stuff. It will be easy as we go into our algebra. But now we're going to talk about something called the distributive law. Which we've seen before. Okay. Distributive law looks like this. If you want to have letters, some number, we'll call it A, general number, times the sum of B plus C is equal to A times B plus A times C. In other words, you can distribute that multiplication process among the terms of the addition. If you want to look at it from a PEMDAS standpoint, what you've done is change from doing the addition first over here, because that's in parentheses. Technically, you'd have to do that first. Then the multiplication. Over here, the multiplication gets done before the addition. So you've changed the order of addition and multiplication, which is not terribly surprising. Because remember, multiplication is repeated addition, so they're kissing cousins, you know? I mean, they're almost identical operations. Therefore, you'd think that something like that would be true. An example would be this. 2 times, let's stick with numbers for right now. 2 times 3 plus 5 is equal to 2 times 3 plus 2 times 5. Calculate it. 3 and 5 is 8. And over here you get a 6 plus a 10. That's 16. Yep, that's 16. That happens with any 3 numbers. By the way, it also happens with negative numbers. Okay, negative or positive makes no difference, fractions, decimals makes no difference. That law holds. Very important in algebra for the following reason. That in algebra, here's the algebra version of it. We're going to put in some unknowns. Again, I ask you to remember, a letter simply stands for a number you don't yet know. Okay? Which means we're going to treat all the letters the same way we treat the numbers. So there's no special treatment going on here. Suppose I have something like this. Suppose I have a 3 times 4 plus x. What's x? I don't know. It's part of a problem. As I go through the problem, maybe at some point I'll know what x is. That's called solving the problem, but we're not there yet. Okay, right now I want to write this in a different way. Right now it's written as a product of two things. 3, the number 3, and this thing in parentheses, which is called 4 plus x. We want to write it in a different way. I'm going to bring that 3 inside, making sure that both of these things that are added in here get multiplied by the 3. 3 times 4 plus 3 times x. Now I can calculate that, so that gives me a 12 plus 3x. So this is a different form of this. And you'll find in algebra that you sort of bounce back and forth between these two forms. For some purposes, this is much more useful. For some purposes, this is much more useful. So it just depends on what the problem is. That's the algebra version of the distributive law. Now, your book, of course, is going to give you several examples, which make it a little bit harder. Suppose we have 2 multiplied by 3y minus 5z plus 1. Well, the distributive law is true no matter how many things you've got inside the parentheses. In this case, we have 3 things. One's subtracted, one's added. There are 3 things going on there. It doesn't matter. Distributive law still holds. So we're going to take that multiplication by 2 and distribute it among these terms here. So it's 2 times 3y minus 2 times 5z plus 2 times 1. Notice everything inside got multiplied by 2. Okay? Now you go back and make this look pretty. 2 times 3, we know this is associative law, actually, for multiplication. We can associate the multiplication with any 2 we want, so let's multiply the 2 times the 3. That would give us a 6y. And this is a 2 times 5, 10z, and of course that's just 2. That's it. That's the new expression. You can even do it with fractions. Let's look at some examples with fractions. Suppose you had 2/3 multiplied by 6 times p plus 1/4. Okay, the fact that they're fractions doesn't change a thing. We still bring that multiplication inside. So 2 comes in, multiplies that, and it also multiplies that. 2/3 times 6p plus 2/3 times 1/4. If you want to, you can think of the 6p as 6p over 1 to give it a denominator.
But isn't that confusing? Because see, then you're just gonna start lowering it, like finding the.
I'm going to cancel things here.
Yes.
Yeah.
But
It's not confusing.
no, but what I mean is that. Okay, never mind.
Okay. I won't. All right. 3 into 3 is 1, 3 into 6 is 2, huh? Okay, cancel. All right, so here I've got a 2 times p, that would be 4p, and 1 times 1, which is just a denominator of 1, that's all. Here we cancel also. 1, 2. Remember, you can cancel when you're multiplying. You cannot cancel when you're adding or subtracting, okay? So here we go, 1 times 1 on the top, 2 times 3 is 6 on the bottom. So here's the new version of all that. Instead of this, we have this. Okay, let's bounce it up a little bit. Now suppose the number that we're multiplying by is negative. Now we have to be careful. Okay? And I'll give you the version that the book provides because it's the safest way to go. It may not be the quickest way to go, but it's the safest way. In other words, it reduces the chance that you get a wrong answer. So this is worthwhile. What they say is, okay, what we want to do is take -8 and bring it in and multiply everything by a -8. But notice you got a subtraction going on there. That makes things a bit more dicey. So we're going to take the -8 and multiply it by the 2. That's easy enough. I'm going to change this to addition of the opposite. Subtraction is addition of the opposite. Agreed? That's what we raised our hand and said, yeah, we're not going to subtract anymore, right? Okay. The opposite of 5y is -5y. It's the same as an opposite of a number. It's just a minus sign in front of it, that's all. So this all of a sudden will become plus a -8 times a -5y. Okay? Now this is important. This gives you a -16 here. This becomes a minus times a minus is a plus 40y. Notice that's a plus. Okay? We had a minus up there, it's now a plus because we changed to addition of the opposite. Keeping these signs straight is important. That's what most people lose points on. Okay? Now some people, you say, oh, well, I know how to do this, I've done it a million times. Yeah. All right, so that gives you a -16. Yeah, that's for sure. That's easy enough. Here, minus times a minus is a plus, and that's, okay, 40y. All right, fine. That's good. If you're real good at it, real practiced at it, you don't have to go through all that change to addition of the opposite stuff. What I'd suggest is if you're new at this, or you didn't do so well the last time you did this, use it. Okay? Once you get proficient at it, yes, you can jump to that. Okay? But sometimes slowing down is a good idea. Let's see if we have something. Oh, here's a nice one. Suppose we have this. Now, I'm not even going to say it. I'll just leave it up there so you can glorify in it. Yeah, to begin with, what does that mean? What's it about? That's a good question. Generally speaking, when you put a minus sign in front of something, you're talking about the opposite of it. Okay? Now let's look at the opposite of a number. If I have 4 and I want the opposite of it, it's the number on the other side of 0, the same distance away, it would be a -4, right? That's okay. Suppose I had -11 and I want the opposite of -11. That would be the number on the other side of 0, the same distance away, that becomes a +11, huh? Okay? Notice what happens with opposites. You can get the opposite simply by multiplying by -1. That will do it, right? The opposite of 4, I'll write it like this. The opposite of 4 is -1 times 4, which is -4. Check it over here. The opposite of -11 is -1 times -11, which is 11. Minus times a minus is a plus, huh? So the opposite of something is obtained by multiplying it by -1. Therefore, up there, what you want to do is learn how to multiply a -1 through all this stuff. -4a plus b plus 3c. Okay, now that we know it's a distributive law, yeah, okay, let's do it. Bring that in, make sure everything in sight gets multiplied by -1. Now let's be careful again. What's inside? Sometimes you have to slow down and say, what is in those parentheses? Actually, nothing but addition. That's already all addition. There's no subtraction there. That is a negative number. That's a -4. There's no subtraction. Okay? Addition, addition. All right? All right, so let's bring it in. -1 gets multiplied by a -4a. Added to a -1 multiplied by b. Added to a -1 multiplied by 3c. Now we go back and finish the job. Here we've got 3 things multiplied together, huh? And of course, we do 2 at a time, so it'd be a -1 times a -4, which gives you a plus 4a. Now here, I have -1 times b. Well, the only thing that could be would be a minus b. So, minus b. Here I have a -1 times 3c. Well, a -1 times a 3 is a minus 3c. All right, now this is this combination of things going on here, this plus minus stuff. It's not that it's wrong, it's just considered bad form. You know, it's confusing. If you hadn't had an algebra course, you'd probably say, what are you talking about? Is it plus or minus? You know, figure it out. So what we're going to do, remember, we decided to change subtraction to addition to the opposite. Okay. You can also change addition to subtraction of the opposite. It goes both ways. So what I'm going to do is this. I'm going to say this is 4a. Now I'm going to change that operation back to subtraction of the opposite of minus b, which is plus b. Subtraction, the opposite of minus 3c is plus 3c. And there's the final answer. That's the simplest form. Now, you're probably saying, oh, that's an awful lot of stuff to remember. It is. That's true. There's a lot going on there. However, now we get to the easy part. And the easy part is you can do it extremely quickly. All right. Here you were asked to get the opposite of this thing, right? Let's look at the thing again. Let's just look at the signs, irrespective of whether they're addition or change sign or negative, or just look at the signs. Minus, plus, plus. Agreed? Okay, this is one of the very few quick tricks I've ever told you, right? What's the signs here? Plus, minus, minus. They flip. That's it. That's all multiplying by -1 does. It simply flips the signs. That's it. So we could have done the whole thing in one step. Wow. Okay? I want to see smiles. All you quick trick people, come on, smile. That's nice, right? That just saved you a whole lot of time, right? Not to mention that, you know, oh, my brain hurts, I'm thinking too much. Right. All right. So you can do it that quickly. That's the only case where, well, it's not the only case. All right, that's section 11.1. We finally finished it. Now we want to go on to 11.2, where we're going to talk about things called like terms. All right. This particular thing, this distributive law thing that we've been doing today, there's nothing more important than algebra. And the reason is this. When you're dealing with a real world problem, very often the information comes to you in English sentences, and English sentences are not known for logic, you know, they're not known for clarity. You just sort of get a sentence here about this, oh, by the way, we measured that, it's this over here, and you get a lot of input. You've got to organize it and put it in a mathematical form. That's what you get paid for. And so often, what comes in is strung out like this. You know, well, you want this, which represents maybe temperature, and this represents humidity, you know these things. And you just get these strings of information. It's useful, and with the right mathematics, you can get some real solutions. But it's just sort of typical English presentation. So the first thing you've got to do is to begin to simplify that information, get it in a nice, neat, compact form, and then you can get some answers. And distributive law is one of the most powerful steps in doing that. So don't ignore this thing. When you get to algebra, this is the real emphasis, is distributive law. Okay. Then I'll offer something completely different. It's my pipe. Right. More terms, definitions. We talked about algebraic expressions. But let's put it up here again because that's going to be our starting point. Algebraic expressions are the sum of one or more terms. Therefore, a term, going too fast here, a term is something that is added. That's what a term is, something that is added. Okay? A factor is something that is multiplied. An algebraic expression, the sum of one or more terms, might look like this. Suppose you have 2 times x plus 5. Okay. One term is called 2 times x, the other one's called 5. This one is known as a constant term. We had some of this yesterday. Obviously, it doesn't change. It's always 5. That's the way it is. This is known as a variable term because it's got a letter in it. It can vary. But let's look at this variable term a little more closely. Notice it's a product. It's a product of a number, and that number is called a coefficient. This is algebra terminology, coefficient, and a variable. In this case, the variable is called x. Okay? So the coefficient here is 2, and a constant is 5. All stuff we have to speak. We all have to talk the same language. All right, now, one of the things that happens in the preliminary stages of solving an algebra problem is what's called simplification. Before we can actually solve, we have to simplify things. And there are several things that help with simplification. One we just did, distributive law. Distributing a multiplication among terms of an addition. The second thing is what's called like terms. Now, like terms are terms, they're things that are added, that have the same variable to the same power. When I mean power, I mean exponent. For example, suppose we have 3x squared plus 5x squared. Those are called like terms. Same letter, x, same power, 2. Okay? Now notice the coefficients are different. Like terms has nothing to do with the coefficients. They can be completely different. But the power and the variable have to be exactly the same, they have to be identical. This is called the FedEx problem. FedEx comes along, drops off 3 boxes of widgets right there. We don't know what a widget is, but we've got 3 boxes of them. And he comes back a few minutes later and says, sorry, there's more. Drops off 5 boxes of widgets again. We still don't know what a widget is, but now we know we have 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay? So we have some mathematical understanding, even though we still don't know what the unknown is. The unknown thing, the widget, we don't know what it is. But we know we've got 8 boxes. And that's what happened with like terms. Like terms can be combined. And that's the important thing. Can be combined. How do you combine them? It's sort of using the distributive law backwards. I erased it, but it was like this. A times the sum of B plus C is equal to A times B plus A times C. We were using it going that way just a few minutes ago. It also goes the other way. When you've got an equation, you can go either direction. And what this side says is you've got a common factor in two terms, you can pull it out and write it as a product of that common factor, A in this case, multiplied by what you might call the leftover factors, B and C. So over here, I've got a common factor in these two terms. It's called x squared. I'm going to pull it out. I'll pull it out on the right. You can pull it out on the right or the left. It doesn't make any difference. All right, here it's multiplied by a 3, and then I have added to that the same thing multiplied by a 5. Oh, so I end up just adding the two coefficients. 8x squared. This is called combining like terms. Obviously, it simplifies things. And that's the whole goal here, is get things as simple as possible. Let's do a bunch of these. But before we do that, there's a list on the bottom of page 641. Let's look at a few of these. The question is, are these like terms or unlike terms? 18AB and 4BA. Is that like? I hear a yes. Anyone agree? Yeah, it is. These are like terms. Why? Because you got the same letters to the same power. Now, the fact that you got two unknowns here really doesn't change the definition. They still are the same in both of these terms. Now, the fact that the multiplication is reversed is simply the fact that multiplication is commutative, and that's okay. So in other words, AB does equal BA. There's no question about that. It's not a problem. So yes, these are like terms. Things that are not like terms might look something like this. Suppose you had 7m squared n to the fifth and 3m n to the fifth. Okay, well the n to the fifth is okay in both of them, but the m squared here and the m there, gotta have the same power. This is only to the first power, that's the second power. These are not like terms, they can't be combined. Okay, let's look at some examples of combining like terms. All right, let's start with this one. Minus 15w plus 4w's minus w. So we've got several things going on. We've got addition and subtraction, all of which is fine as far as distributive law is concerned. Notice every one of these things has the same variable w to the same power. It's the first power, which we never write. Okay, so according to what we just said, you can pull the w out. Here it's multiplied by a minus 15. Added to that is a plus 4 of these things, and then you subtract 1. Remember, there's that invisible 1 that multiplies everything. There's one w there, and you're subtracting 1 w. So a minus 15 plus 4 is a minus 11. And then subtract 1 takes you down to minus 12. Minus 12. This is a lot easier to work with than that. Simplifying. Here's another one. Okay, we've got two unknowns, x and y. The fact that the letters are different means they're not the same idea, they're not the same concept. So you don't dare combine x and y, so that would be foolish. Okay. However, we have two terms with x's in them and two terms with y's in them. Okay, those are the like terms. The same variable, same power. So if we pull the x out of these two, here it would be multiplied by a minus 3, and to that we would add 4. And then we also have the y's here. Let's pull the y out. Here it's multiplied by 8. And then we subtract 10. And then we've also got this constant hanging off on the end there, 19. All right, minus 3 added to 4. 1x. We don't write the 1. It's 1 coefficient in the derivative. 8 minus 10, that's going to be a minus 2y, and then minus 19. Now again, we run into this plus minus problem. That would be a poor way to leave it. So what we say is, okay, I can get rid of that by changing the addition into subtraction, but I have to change that to the opposite. So that's going to be an x minus 2y minus 19. So we're reducing the number of terms by combining like terms. That's the idea. You can do it even with decimals and so forth. 0.2a minus 1.4 plus 1.4a minus 6b minus 2.1. Okay? Decimal coefficients. Actually, in the real world, most of the measurements made in time and space in the real world are decimal measurements. Because just like your calculators, the decimal machine, the thing that measures, let's say, distance going across a room or going across a campus or something like that, it's a laser. And what's it connected to? Decimals. And the readout, decimal. Feet, yards, but it's decimal. So this is much more like what a real algebra expression looks like. You know, we work with, you know, whole numbers and fractions once in a while, but that's the way the world works. Okay. Are there like terms? Sure. This one and this one are like, and this one and this one are like. Why? Because these are just decimal numbers. All numbers are like terms. So you can always combine numbers. All right, so let's look at the A ones. These are both A's. Here you got 0.2, and then added to that is a 1.4. Now the B is just B. There's only one term there, nothing to consider. But then we also have minus 1.4 minus 2.1. All right, doing the arithmetic on this adds 0.2, gives you 1.6a minus 6b. Now here, how would we do this? Well, probably the easiest thing to do is to change it to addition of the opposite. We've got minus 1.4 added to a minus 2.1, which gives us a net of, that would be add the two absolute values, attach the common sign. That would be minus 0.5, 3.5. And there's your result. Combining like terms. Constants are like terms. All right. So this is section 11.3, which will not be on your test tomorrow. Your test goes through 11.1. So chapter 10 and 11.1. So this is the homework for Monday.